Hello, everyone. Right. So super glad to see so many of you here in this room. I am Aurimas Griciūnas. I am a senior solutions architect at Neptune AI. And if you don't know what Neptune AI is, it is an experiment tracker, or rather a general machine learning metadata store that you can use to supercharge your machine learning model building process. I'm also a CEO and founder at Swirl AI, where we help companies and professionals to make out of their data assets as much as possible. And today, I want to give a talk about MLOps fundamentals. So it will be a fundamental talk, so a relatively high-level talk. It's named what every machine learning engineer should know, but actually it generalizes very well to any data professional. So I'll start with it. So yeah, for me, MLOps is a function of many things, and the output of this function is relatively generally agreed upon, and it is machine learning development velocity. So basically, we are trying to do what DevOps does for regular software, but for machine learning systems. And this is also about scaling machine learning, but when it comes to scaling, it's not vertical scaling, but rather horizontal scaling. So deploying a service to handle more and more requests per second is something that we solve by software engineering. This is more about how many machine learning products we can actually deliver in as short amount of time as possible with as little amount of people involved. And when it comes to the inputs of the function, because inputs are the only thing that we can actually influence, I'm talking about things like organizational structure and maturity, processes, tools, and time. And I kind of, in this talk, want to touch upon most of them in a holistic way and how they interact with each other and how we can structure both our organizations and processes to achieve the highest machine learning development velocity. So why do we even need a new term, MLOps, right? We already have DevOps, and most of the people are saying that machine learning systems are not that different when compared to software systems, but they are to some extent. So regular software is pretty deterministic. We kind of hard code rules that we expect to be applied on top of the data, and we already, by doing so, know what output to expect from a regular software system. When it comes to machine learning, though, it's a little bit more complicated because there is a lot of dependencies on the data itself. So what data is used to produce the model, and the nature of the data itself is also stochastic. So it's really hard to say what kind of outputs the model will produce. So one of the things that can happen is so-called data distribution shifts and training serving skews. And a very short reminder of what that means. So it's basically a difference between data that we use during our training processes and our inference processes. So let's say we are training data on a given population which has a certain distribution, and when we deploy the model into production, and we expect it to behave in a certain way. And it does for some time. However, as the time goes, our population starts to drift. A very good example is we are running a website in the recommendation system, and for example, our users start aging, right? And different age groups start appearing that use our website, or we are deploying our website in different countries, right? And what will happen? The outputs and the expected outputs of your machine learning models start to drift, meaning that we do not produce good enough results anymore. Another type of data-related issues that can happen is the so-called training serving skew when it comes to data assets. So it might happen that the model that you are deploying is already deployed on a different population when it was trained on. And a very good example here would be you're training your computer vision model, segmentation model, for a tool defects, and you're training in a very well-lit environment, but then you're deploying your model in a factory which is not well-lit anymore, and your machine learning models stop predicting accurately right from the get-go. Another type of skews is technology-related ones. For example, you're training on Python, you're deploying on Go, You're also doing pre-processing in Python and pre-processing in Go. Once you deploy your machine learning model into production, it starts misbehaving from a get-go. Another culprit that we solve for when doing MLOps is how the machine learning project lifecycle itself looks like. So from DevOps, we know that from DevOps best practices, we know that one of the main aspects of a project that you need to take care of is feedback loops and handovers. And we know that in order for the project to actually be efficiently developed and improved, we need to have both artifact console handovers and feedback loops encapsulated into a single team. And machine learning project lifecycle looks like this. So we have an ideation stage where subject matter experts, data scientists, and project managers, maybe some data engineers as well, sit down in a single room. We brainstorm on a problem that we have. We decide if we need a machine learning model. If we do, we move to the next stage. If we don't try to use machine learning because you will increase your costs unnecessarily. Next stage, data scientists experiment. We build model POCs. We experiment on the data assets that we have. We choose several architectures of machine learning model that we want to train, different combinations of hyperparameters. Once something of a value is created, it is handed over to the next stage, which is deployment. So we hand over a trained model artifact in the form of binary to be deployed. Machine learning engineers pick it up, package them into a machine learning system, which is not only a binary anymore, but rather a fully packaged solution, which includes monitoring, logging, and implementation of feedback loops. And at this stage, which is monitoring, we start creating these feedback loops. First is from monitoring stage to deployment stage, and this involves two types of feedback loops. The first type is a regular software engineering type of feedback loop, so application metrics like latencies, response codes, application logs, etc., just to see if everything is working correctly in production. Another one is strictly connected to machine learning projects, and this includes solving problems about which we talked about in previous slides, so data distribution shifts. So we monitor for these, and if something out of the ordinary starts to happen, we retrain the model. And it's important because we don't need to create this feedback loop from monitoring to experimentation, because the only thing usually what you need to do once a training serving skew happens or data distribution shift happens is retrain the model. So you don't need to go back to experimentation stage. And the last feedback loop is from monitoring to experimentation. Here is where we have online testing, so things like A/B testing, interleaving experiments, or multi-arm bandits. So we pin two models against each other. Whichever wins is then promoted to run in production, and we pin a new developed model against it. As mentioned before, both development and feedback loops have to be encapsulated into a single team when it comes to efficient model development. So these are team boundaries. And these are what we call end-to-end machine learning teams, composed of data scientists and machine learning engineers. If we place them into a single team, they're capable to do all of this on their own without needing any additional software engineering help. So what is important in this life cycle? How does it look like when we look a little bit closer into it? So in the very low MLOps maturity environments, what we usually have, this is a very simple representation of machine learning training pipeline. It is a lot more complicated usually. So here we have the exploratory data analysis, some pre-processing. We train a model, evaluate it, validate it. Usually you would have some branches happening here, so maybe even few models are trained by a single pipeline. You have data scientists working in this experimentation environment. And then, as we like to call it, once the model is produced, we throw it over the wall into a model deployment stage where machine learning engineers take over and deploy a model to production. And this is also where misconception usually happens when people think that software engineering is like when we think that machine learning systems are the same as software systems, because the deployment stage is really simple. We can deploy our models in 4 main ways. So it's a batch deployment where we encapsulate our machine learning model as a distributed application or non-distributed application, so Spark or just Python. We extract some data set from our batch storage, apply inference, push it back to another batch storage, which can be synced with real-time capable, serving capable storage like Redis, and then backend services connect to these inference result stores directly and do what we want to do with inference results that are provided by machine learning models. Then we have stream, embedded in the stream application deployment models, where we encapsulate the model into a streaming framework. In this case, I noted the notified Flink here because it's very popular nowadays, since streaming applications are also becoming more and more popular. So this application subscribes to one of the feature set streams, applies inference, and pushes it down the stream to an inference store, which usually is in the form of another stream, and backend services can then subscribe to this stream directly and use these inference results for their downstream use cases. Then we have real-time, where we encapsulate our model as a backend service, expose it via gRPC, for example, endpoint, slap a load balancer in between the machine learning service and backend services, and backend services are then able to request the inference result in real time. Then we of course have edge or embedded deployment, very popular in the latest, I would say, years, probably months. It provides some very big benefits, like security ones, because data does not need to leave devices anymore. Plus, latency is almost non-existent because the data does not have to travel through the network. But it is a lot more complicated to deploy your machine learning model in this method. So one important, maybe also point in all of these is that the models rely on data heavily, and the data is stochastic. So even though the models themselves are deployed as a regular software, they are still dependent on the data that is being fed into them and the monitoring that is different compared to software engineering systems. So how does a high MLOps maturity, what I would say the final goal of a company doing MLOps should look like? This slide encapsulates what is so-called CICD CT process. And CICD we really well know from software engineering systems, so it's continuous integration and continuous delivery. It is different for for machine learning systems compared to regular software systems. And then we have additional step which is CT, so continuous training, which we usually don't have in regular software systems. So how do we start? So we have a regular experimentation environment at the very top. Data scientists can access raw data and graded data. So raw data and graded data is no longer a responsibility of data scientists, it's a data engineering domain. Then we are able to do exploratory analysis on these. We have a regular machine learning training pipeline. We simply remove model handover, so we do not throw the model over the wall anymore. We also introduce feature store. Feature store allows us to avoid any training serving queues when it comes to data and technology, because we pre-process data once and we allow it to be used both in experimentation environments and production environments. Very and most probably important thing that we introduced here is that we no longer treat a model binary as an artifact that we'll be deploying, and rather we treat the entire pipeline as an artifact also. And it becomes part of our code versioning systems. And this is where CI already is different compared to what it is in regular software systems, because we test the entire pipeline, so we can test the code of the pipeline or how it integrates with other environments. We can test each of the steps separately, because usually they would also be deployed in separate environments. We can do unit tests as for similarly like for regular software, but we will also need to do integration tests, like to see if each of the steps integrates with previous step, and if, for example, the pipeline is able to integrate with the feature store. It's noted here that it's the artifact storage that eventually the pipeline is saved to, but usually it's more of a just a code history that you're storing your pipeline in. The next step is CD for the pipeline. We deploy the pipeline into production environment and make it accessible by our tools as a triggerable pipeline, or we might also want to trigger it as we put it into that environment instantly. Additional things that we need is the machine learning metadata store. By the way, Neptune AI covers this space very well. We store data like dataset versions, model types, hyperparameters that were used to produce a model, any performance metrics that were produced by a model, etc. Then we store the model into the model registry. Usually, these systems provide a convenient user interface where you can go into, explore your experiments, switch model state from staging to production. Once you do that, a continuous deployment pipeline is being triggered by this system, and then you deploy the model binary from it to a deployment environment. In this case, I noted here Kubernetes, but it can be actually anything almost that can deploy a model. Additional piece in this diagram that we are missing is monitoring system. So we need to output any metrics that we want from production environment so that we are able to react on them. And then the orchestrator, which we can trigger either automatically by the monitoring system or ad hoc by a person, or just simply on a cron, let's say every 1 day. And it re-triggers the pipeline in production. And this is where we achieve the continuous training part. And continuous training is very important because the main thing that it allows you to do is, of course, automate your pipelines in production, but then you're freeing up the resources of data scientists because they can continue developing other models and building other models while we can very easily re-trigger their training in production. So it's very good that this entire workflow is split by a function. So we have feature platforms, pipeline frameworks, metadata stores, and deployment and observability. And the SaaS vendors are split also very nicely. So we have stuff like Decton, Feast, OpsWorks, or Feature Forum for feature platforms. We have ZenML, Kubeflow, Dexter, Airflow for pipeline frameworks, metadata stores as Neptune AI, MLflow, or weights and biases. And then deployment and observability, examples Kubeflow, Seldom Product, SageMaker, Endpoints, and similar. So how do we enable this small team to handle all of this? We do that by introducing some support, and we can do it by introducing machine learning platforms and machine learning teams that provide capabilities that were mentioned in the previous slide. So we now have two types of teams. We have end-to-end machine learning teams, and we have machine learning platform teams working as a unison. And once we have that, one more mention of very important aspect is the monitoring from the feedback loop from monitoring to experimentation, which we haven't touched yet because the previous diagram only explores feedback loops from monitoring to deployment. So this is not the only thing that we need to monitor. As I mentioned previously, there are also A/B tests. So last slide, and very important to grasp, is that machine learning systems are only a part of a bigger software system. So if we implemented everything correctly, we would have something like this. So we have end-to-end machine learning team building machine learning systems that expose machine learning services, and we build all of this on machine learning platform. And then there is a product team in between, which also builds a backend service that then retrieves inference results in real time from the machine learning service that are then exposed through a front-end service to the end user. And the last feedback loop, which is online testing, is actually this. So we need data from end user flowing back to our end-to-end machine learning platform, machine learning teams. And the problem is here is that machine learning platforms are built on top of developer platforms usually. And the A/B testing and the online testing capability is usually part of developer platforms. So in order to make this end-to-end flow of work, we need to introduce a very convenient way for machine learning, end-to-end machine learning teams to be able to deploy certain machine learning models and combinations of them, protection themselves. So marrying of machine learning platform with developer platform needs to happen. And this is all I had for today. Once again, my name is Aurimas Griciūnas. You can follow me on LinkedIn, and you can also subscribe to my newsletter. I write about machine learning, data engineering, and overall data-related topics. So if you're interested, please do so.
So we have a couple of more minutes for any questions.
Thanks, Aurimas. So a bit of a general question, but how do you imagine or envision the MLOps field going forward? For example, do you expect some tools like to merge together into some bigger solutions, or do you expect them to become more specialized and like clear leaders emerge?
So we kind of already have solutions that cover everything. So bigger platforms like everything that clouds provide, or even HopsWorks one. We are covering more than just a piece of that diagram. And I think that the MLOps maturity when it comes to tooling is already high enough. So we already have tools to implement all of this. The main problems are organizational and team structure related rather than tooling related. I don't think that there is a need to merge these segments, but it will unavoidably happen, probably as tools like, for example, even MLflow itself. Like it already covers more than just experiment tracking and model registry. It already has packaging and pipelines, right? So there are probably too many capabilities that you could work on as a SaaS tool, and you will probably work on them because you will exhaust all of the things that are needed in your focused niche, I think. So eventually, probably, yeah, they will merge to some extent.
Thanks.
Go ahead.
What about explainers for models? Is it an engineer's responsibility, or is it for data scientists in MLOps?
It really depends, but I would say that it should fall under data scientists because machine learning engineers are usually more of a concerned about automation of things rather than actually, because explainers usually you would also go back to your IDE or Jupyter Notebook, for example.
For example, with highly integrated tools like in-depth financials, you have to explain all your predictions, so that should be also.
Yeah, so that's falls in the same category, but then it's definitely data scientists because it's a lot more analytics focused task rather than automation focused task.
You mentioned deployment on edge devices is a complex thing. In your opinion, what are the main challenges while doing this?
Yeah, so the main challenge probably is that you need to transform most of the models that you build into a more compact version. So you do things like quantization and knowledge distillation are similar to just reduce the size of the model, that it fits on the device. And during these procedures, usually you will need additional testing and quality gate pipeline because the accuracy also changes. So whatever you trained initially might not be as good when compressed, right? But this is one part of them. Of course, you need to distribute your applications to the devices in a certain way. But usually it's just a longer pipeline because of the fact that you need to make your model smaller. Plus, you can't monitor it as easily because the data is inside of the device. So you will not be able to get any monitoring results out of it. So you will have to rely on the capabilities of your model and it's not drifting away, right?
Thank you.
So thank you very much, Aurimas.